Okay, we're continuing on here. And we are in chapter 14. We are on the back of organic here, almost done with all that organicness. So last time we talked about a couple of important groups. We talked about the carboxylic acid. And the carboxylic acid has a functional group of carbon, oxygen, double bond, OH. And we also talked about esters, which have carbon, double bonded oxygen to a carbon. And these here are named with oic acid at the end of it. So you kind of drop the A off of the alkane and go oic acid. Much like the aldehyde, like we talked about here, it does have the hydrogen here at the end, which means that it will always have to be at the end of the molecule, that functional group. So you do not need to give the location in terms of the name. But in terms of numbering, this will always be carbon number 1 in terms of numbering. So if we have something like ethanoic acid, that is a 2-carbon group, like so. Looks something like that. For esters, it is named as sort of an alkyl group. And you then end with O8 at the end of it. And really remember that with an ester, if you break it right around here, if you go away from the double bond, that is your alcohol sort of part of it, as these guys are made from a combination of an alcohol and a carboxylic acid in an esterification reaction. And if you go towards the double bonded oxygen there, that is going to be your carboxylic acid part. And remember, carboxylic acid part is really the one that gives the base of the name. So however many carbons are attached there. The alcohol part is the part that is named like an alkyl group. So if you had something like this, once again, if we broke it here, that's our carboxylic acid group, which has 1, 2, and 3 carbons. So that's going to be propanoate. And here, the alcohol part. And that has just 1 carbon group, which is methyl. And then again, we put it here together, the group first, and then the O8 there gives us methyl propanoate. Any questions on that? And again, this is a result of an esterification reaction where we take a carboxylic acid and we add an alcohol to it. And we basically remove water here. So if you remember, just kind of remove water there. And then we just kind of put everybody together to give us our ester. The bond in the ester, always that carbon double bonded oxygen to a carbon. And that will give us our ester in this particular case here. We also talked about a number of times how we get to a carboxylic acid that originates from a primary alcohol that gets oxidized to an aldehyde, and then that aldehyde gets oxidized one more time and makes the carboxylic acid group there. So that is the pathway that we talked about. We're going to talk about alcohols, obviously, there, and also aldehydes. That's how we get to a carboxylic acid. Any questions on any of that there? Okay. All right. Then let us continue on here. So as we talked about, esters are responsible for a lot of fragrances and perfumes. Smells, also flavors as well, are as a result of these esters. And here are a table from your book of some esters. And again, this guy here, which is propylethanoate, responsible for pears. Bananas here, pentyl ethanoate. Again, here is our ester bond. Going this way on all of these here is our alcohol part. Going the other way is our carboxylic acid part. going in this direction. So again, 3 carbons, propyl, 2 carbons, ethanoate. Yeah. Here we have 1, 2, 3, 4, 5 carbons, which is pentyl, 2 carbons, ethanoate, and so forth. Here's oranges, a big old alcohol chain there, basically of 1, 2, 3, 4, 5, 6, 7, 8 carbons, octyl, and 2 carbons there for our ethanoate, obviously pineapple and apricots as well. So these esters, again, is responsible for a lot of flavoring, also a lot of smells and aromas that come about as well. All right, so why don't you draw these guys here? Why don't we also do, let's do 4-methyl octanoic acid. And let's do butyl. No. Let's do butyl pentanoate. All right, so why don't you draw those guys, see what you come up with here. That's butyl pentanoate, yeah. Look here and see how you're doing. We'll start the first one, which is 3-bromol butanoic acid. So as always, we're going to kind of work our way backwards. So the oic acid part there tells us it's definitely a carboxylic acid. The butane part tells us it's 4 carbons. So that's where we're going to kind of start with. Remember, once again, since you're drawing it, you really could put the carboxylic acid group on either side. I will put it here on the right, but you could just as easily put it there on the left. Because I put mine on the right, that would make that carbon number 1 for me. Obviously, if you put it on the left, then your carbon number 1 would be on the left. And that's important because we do at carbon number 3 have a bromine group. And for me, right here would be carbon number 3. And then that's pretty much everybody. Now we just need to kind of fill in our hydrogens here. And here we would go with 2, we'd go with 1 and 3 in this case. And this would be our condensed formula, obviously, for this molecule. Again, we're an acid draw the line structure, but again, could kind of work the same way. 1, 2, 3, and 4. Once again, we can put our carboxylic acid group in there. This would be carbon 1 for me. 2 and 3, and then we would have a bromine. If we did more of a line structure, it would look something like that. So condensed on the bottom there, line structure up on top. Any questions on that one there? Coming to B, which is ethyl propanoate. Once again, when I see that O8, should tell me it's an ester, and it does have basically 3 carbons on the carboxylic acid side. So as we talked about last time, again with esters here, kind of like ethers, you may just want to kind of start with the kind of functional group connection and then just kind of fill in what you need on each side. Remember that as we go sort of this way towards the double bond, that is our carboxylic acid part. And that is where this part basically comes from, right? So propane means I have 3 carbons. I already have 1 there, so I would just need to add a couple more to give me 3 total. And then this part is the alcohol part, which is going away from that. So that's the alcohol part. And that's ethyl, which is 2 carbons, which would go this way. And now we can just fill in our hydrogens there. So 3, 2, 2, and 3 in this case. Any questions on that one there? All right. So coming to the next one, octanoic acid, bad choice. That is a carboxylic acid, and that tells us octane is 8 carbons. I regret my decision very quickly here. That's 3, that's 4, that's 5, that's 6, that's 7. Yeah, we'll go this way. That's 8. I'm going to actually throw my carboxylic acid group on this end because I don't feel like I have a lot of room on the other end there. So because I did it on this end, that would be carbon number 1 for me in this case. Obviously, if you threw it on the other end, that's going to be your carbon number 1. And that means for me, carbon number 4 would be here. And that would be a methyl group. You could put it up on top and just can go on the bottom so I have a little bit more room. And at that point, we're pretty much done with all the name. We're just going to fill in our hydrogens here. So I do need 2 there. I do need 2 there. Here I only need 1 as it already has 3 bonds. Here I need 2. I need 2 and 2 and 3 in this case. Any questions on that one there? Lastly, we got O8 tells us is an ester. And that means we're going to start with our, I'll go here maybe. Going to start with our ester group. And once again, going in this direction towards that double bond, that's where we're going to go here. And that's going to be 5, which means I got 1 there, 2, 3, 4, and we'll go down a little bit, 5. And obviously going the other way is our alcohol, which comes from that part, and that's 4. 1, 2, 3, 4, a little tight there. So maybe we'll go, erase that name and just draw it above it, maybe. All right, so we got 1, 2, 3, 4, 5, and 1, 2, 3. Still run out of room. That's even worse. All right, so we'll go 4. All right, and we'll just fill this guy in at this point. All right, so we'll go 3 there, 2 there, 2 there, 2 there. We need 2 there, 2 there, 2 there, and 2 there. We're out of room here. All right. Any questions on those structures there? Obviously, that should be a 3 at the end there. At the very last one should be 3. Try one more time here. Try not to, I'm going to start way left here. Try not to screw it up one more time. All right. All right, one more time with meeting here. CH3, CH2, 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 C double bond O, O, CH2, 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 and CH3. Yeah, there we go. Any questions on that one there? Oops. Questions on any of them? Yeah. Apparently plan for more space, I guess, as a drawing. All right. Then we're going to continue on. So we've talked about obviously how we make esters, which is an esterification reaction. And we make esters obviously by removing water and kind of putting both the alcohol and the carboxylic acid together. So maybe no surprise, hydrolysis of an ester is basically just breaking it back apart. And we take water out to put it together. We do oftentimes put water in an occasion back to rebuild it. But a hydrolysis reaction can actually occur in 2 different ways. We could have an acid hydrolysis. We could also have a base hydrolysis that we will see. So we're going to first talk about an acid hydrolysis. And hydrolysis basically means water. So it basically means you're just going to pop some water in there somewhere along the way. So if we have an ester, like the one we see there on the bottom, and we add some water here, and we do this with an acid as a catalyst, and that's what that means, is an acid catalyst and some heat. We will basically break this ester apart, and it's going to kind of break apart exactly kind of how we put it together. So just kind of throw a line right there, and you're going to get basically your 2 parts here. So we will have our carboxylic acid part. I'm just going to kind of go down here. We will have our carboxylic acid part here, and we will have really our alcohol part in this case. And what happens is when we add our water in an acid catalyst, this part of water will be used to recreate our carboxylic acid, which is basically just missing an OH there at the end. And what's left at that point in terms of water is, maybe I'll make it reddish here. We have a hydrogen that will be used to complete our alcohol. So a acid hydrolysis will involve an acid and water, and you will get back both of the things here, a carboxylic acid and an alcohol. You'll get back the original two components that were made up the ester. So this is kind of like the exact opposite, obviously, reaction of the esterification reaction. Gets you back to your two starting components. Questions on that? And clearly it always just breaks apart right at that point and basically rebuild it. Now, if you do this sort of reaction, but what is referred to as a base hydrolysis, sometimes referred to as a saponification reaction, which is a fancy way of saying like kind of how they make soap, basically, is sort of the end result of what happens here. You actually will not get back both pieces that you started with. So in the acid hydrolysis, if the acid is used as a catalyst, you'll get back both the completed carboxylic acid and the completed alcohol. The reason that happens is because it's in an acidic solution. That's what the acid catalyst is used for, and that helps basically put the H back on the carboxylic acid and get it completed to a carboxylic acid. But if you do this in a base conditions with a strong base like sodium hydroxide, you actually will not get back both parts. You'll get close, but you will not get back both parts. So if we take a look at the same sort of ester here, and in this case, we're going to add sodium hydroxide, which is a strong base, and obviously some heat as well. Once again, we are just going to basically break this thing apart in this normal location. That is going to get us basically our two parts here. Now, in this particular case, you will actually still get the alcohol back. So if you want to think about it, you can think about the H here. Not exactly perfectly how that truly works, but the H here will come out and complete our alcohol, which is what we need. Now, clearly, if you look at sodium hydroxide, that's basically a sodium ion and a hydroxide ion. So clearly here, we're borrowing the H there. That really just leaves us a oxygen, and we don't have the other H to get our carboxylic acid back. So what ends up happening here is we actually make a salt, and that salt here is going to be what is left over, and that's an O with a minus, and sometimes they will write the sodium next to it, and that's really a salt here. Well, and we will get our alcohol back. This is essentially how you make soap, except that your carboxylic acid is giantly larger, a ton larger carbons on it and stuff like that, giant change of carbons. And that's what kind of makes soap here. Soap is essentially, as we will see in a later chapter, just a really long chain of carbons and hydrogens. And at the end, you do have this carboxylic acid salt like you make here. And that's what gives soap two parts. Soap has this giant nonpolar part. And this part right here is the polar part of soap. And that's sometimes referred to as the polar head and the nonpolar tail. And that works really well because, as we will talk about, dirt is nonpolar. So what happens when you use soap is the nonpolar part of soap, which is that really long carbon chain, traps all the dirt in it because they will mix together, nonpolar, all good. And it will make what's known as a micelle and create the polar part on the outside, which is really good because now you have trapped all your dirt, which is nonpolar, and you have on the outside here the polar part of soap, which is really good because typically if you use soap, you wash it off with water, which is polar, right? So when you wash it with water, the outside part of soap is going to be attracted to water. It's going to mix really well. Inside is the trapped dirt. You're clean now. Good to know how soap works, I suppose. And now you're nice and clean. And that's basically this process here, using really long chain carbons and hydrogens, is kind of what creates something like soap. Any questions on that there? So two types of hydrolysis reactions here. If you do this with water and an acid, you will get back completed, the exact two things you started with, complete carboxylic acid, complete alcohol. If you do it in the base conditions, you will get just the alcohol back, and you will get close to the carboxylic acid. You'll just get a salt missing a hydrogen, basically. Yeah. Any question there? All right, so why don't you try one here? Why don't you write the reactions if you started with methyl ethanoate and you did water, heat, and an acid catalyst, and you did in B potassium hydroxide and heat. So see. Okay, let's take a look. So we're going to write an equation of what's happening here. So we might as well start with our starting thing, which is methyl ethanoate. So again, that is obviously an ester. So we'll have our ester connection. The ethane part tells us that we got a couple of carbons off the carboxylic acid side. The methyl part tells us we got one carbon off of the alcohol side, and then we'll kind of just fill it in. So this is going to be really our starting guy on each of these reactions. So we'll go and start with that there. So in this case, we're going to react it with water and an acid as a catalyst and a little bit of heat. So this is obviously the hydrolysis reaction. Remember that pretty much the one with the acid and the water is pretty much the opposite of the esterification reaction. So we're just gonna break this apart in its normal location, and that will give us our two parts here. And because I know this is the acid hydrolysis, I do know I'm just going to get back my kind of starting two things, which is the carboxylic acid. So clearly this one needs an OH here to get to a carboxylic acid. And the other one is going to get to the alcohol, which means it needs just the leftover H, if you will. And now we have, again, basically the opposite of putting it together. We got our carboxylic acid back and our ester as well. Any questions on that there? All right, so take a look at the bottom one here. That's KOH, which is potassium hydroxide. That is a strong base. And again, we're going to be starting with our ester, which means we're going to go down the base hydrolysis route here. So I'll just go above maybe. So we'll be starting with the exact same here, except we are going to kind of do a little sodium hydroxide action happening. And not really a line there, sodium hydroxide. And in this case, we are not going to get back. What's that? Oh, it's like sodium. Are you know, just want to see if you're paying attention. It's only my 40-second screw up today. That was good. All right, so we'll go with potassium hydroxide. There we go. I didn't feel it felt right when I was writing it as well. You know, it happens. All right. So we're going to break this guy apart, obviously, in the same location. Can give us really the same parts here. And we're just going to kind of try to put our parts together in the proper way. And on this one, remember, taking the base route, we will get the alcohol back. So if you just kind of keep an accounting of a lot of things, even though it doesn't really truly work exactly like that. The H is going to kind of end up over there. That's going to leave you really that oxygen that's left over. And that is what's going to attach over here to our carboxylic acid, but we don't have the H, so it is going to make this salt. And here we would have a potassium just floating around to balance out the charge. And we will get our salt back of a carboxylic acid, and we will get our alcohol back here. And that is an alcohol up there as well, just in case we're curious. That is an alcohol up there as well. So Acid root, get back both starting materials, base, get one of the back, just the alcohol, and you're left with just the salt. Any questions on that there? All right. That's what hopefully it shows there. Perfect. All right, we're now off to the next second to last organic group, which are amines. And these are nitrogen containing groups. So amines have a functional group of NH2, and that is the functional group. It is a group that is basically related to our friend ammonia. So if you remember, ammonia looks like this. But for an amine, it has this as its functional group. So it has that nitrogen that is present. And that's what we see here and here as well in this particular case. So amines are derivatives of ammonia. In one or more of the hydrogens are replaced with a carbon group or aromatic group. You can also, kind of like carbons, kind of like alcohols as well, you can classify amines as primary, secondary, and tertiary. So we could also classify amines as primary, secondary, or tertiary amines. And you're probably not going to be extremely surprised here, but it is based on how many carbons are attached to the nitrogen in this case. So we got 1, 2, 3 carbons, so we'll have a tertiary. Here we got 1 carbon there, right, which is a primary. And over here we have 1 and 2 carbons attached to the nitrogen, and that would be a secondary amine. So we can classify these just like we do kind of carbons and alcohols and so forth. Here, though, we do have some groups that are attached to the nitrogens, and that sometimes creates some different sort of ways that we maybe name some of these, or different ways you sometimes will see names here. So once again, a primary amine will have 1 carbon group attached to the nitrogen. And again, that's what we see here. Primary 1 carbon, secondary 2 carbons attached to nitrogen, and tertiary 3 carbons attached to the nitrogen in this case. So this also will affect, like I said, sort of how you might go about naming some of these guys, depending on whether it's a primary, secondary, or tertiary amine. Now, because these are nitrogen based, that also, by the way, is a hydrogen that is directly attached to a nitrogen, right? And that means it is the ability to hydrogen bond. So just like ammonia can hydrogen bond, this guy could also hydrogen bond. And remember that you need basically a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine in order to hydrogen bond. So it does have that ability. We can go with sort of common names here for amines. And the way that we do common names is kind of like how we do it with ethers. So here we're going to look at the nitrogen and basically find the carbon group attached to it and put it in alphabetical order. So that would be methylamine. This is the nitrogen that has 2 methyl groups. So that would be dimethylamine. And this is obviously the nitrogen that has 3 methyl groups, and that would be trimethylamine. Obviously, if there are different groups attached, alphabetical order, kind of like what we do with the ethers as well. So simple names, basically just the alkyl group and put amine, and that's how we will really probably name these guys. Is this way. It's not necessarily the IUPAC way of naming, which is a little bit different, but we'll go with this route here. So once again, this is a primary amine. It has a 2 carbon group attached to it, and that is an ethylamine. This is a secondary amine. It has 2 carbons attached to it, and that is dimethylamine. And over here we have 3 carbons attached, which is a tertiary. We have an ethyl group here, and we have 2 methyl groups here. So that gives us ethyl dimethylamine. A reminder that when we do name and there is a prefix, we don't count the prefix in alphabetical. So what we're comparing here again is the ethyl E to the methyl M. So we don't look at the di part of it when you have a prefix in alphabetical order here. So that's why that comes this way. The bottom one is tertiary because this nitrogen's attached to 1, 2, and 3 carbons. Yeah. We do because we're kind of doing sort of almost like a common name for these guys. So basically, what we're looking for is the carbon groups that are directly attached to the nitrogen. And in this case, that's an ethyl group, that's a methyl, and that's a methyl group attached there. And then we put it in alphabetical order. In this case, since we do have 2 methyls, we also use the prefix like dimethyl. Other questions? All right. Why don't you write the common name for each of these and classify them? Why don't you also draw, we'll do ethyl propylamine. Start with the first one here. So this is a nitrogen, and this is the carbon group that's attached. And I see just really 1 carbon attached to the nitrogen. So definitely this should be a primary amine in this case. And we'll go with kind of our common name here. So that's a 3 carbon group, which is based off of propane. So that will be propylamine. Yeah. Any questions on that name there? Coming to this one here, that is a nitrogen that has 1, 2, and 3 carbons directly attached to it. So that's going to be a tertiary amine. And we're going to go common name here. So that clearly is a methyl group. That is a methyl group. And I feel like that's an ethyl group there. There we go. And that's going to give me a ethyl, once again, dimethylamine in this case. Yeah. First off, any questions on the names there or the classifications? We're going to draw it. So clearly I have an amine, which should just tell you nitrogen, right? Again, it is based off of this group right here, right? So in this case, I'm just going to actually start with my nitrogen. And I know that each of these other things are carbon groups that are attached directly to the nitrogen. So propyl means 3. So we'll go 1, 2, and 3. And ethyl is 2, so we'll go 1 and 2. We could put in our hydrogens here. So I need 3, I need 2, I need 2, I need 2, and I need 3. But now I do have a little bit of work on my nitrogen. It also will need a hydrogen. Yeah. So the nitrogen here will need a hydrogen because this is a secondary amine and it will have 1 hydrogen. So how do I know that? Well, I know that because although not oftentimes drawn in these pictures in this book probably, there are 2 lone pairs there on the nitrogen. And since nitrogen is period number 2, it has to obey the octet rule. Which means that is basically 2, 4, 6. So it is missing a bond to get to 8. So kind of like our carbon friend, it will need 1 hydrogen there to get to 8 electrons, just like the octet rule, basically. So a primary amine, as you can see here, has actually 2 hydrogens attached to the nitrogen. A secondary amine, like you see here, has 1 hydrogen attached, and our tertiary amine here has no hydrogens attached, right, to our nitrogen in this case. So you do have to just be a little careful on the hydrogen, and don't forget that the nitrogen may need a hydrogen depending on which one you're drawing. So that's where you could kind of just think about is like octet rule, and just remember there's 2 electron dots and however many bonds, and if you are short 8 electrons, you might need 1 bond. If you're short 4 electrons, you need 2 hydrogens. And that's a good way. If you're not short anything, like if we take a look at just this guy in the middle, he basically has this and those two dots, so 2, 4, 6, and 8. So again, that's why the nitrogen there doesn't need any type of hydrogen. It has met the octet rule. And again, sometimes that's confusing, especially at this level. Sometimes they may not oftentimes draw those dots on the nitrogen, so you just got to remember that they are there. Yeah. Any questions on that there? All right, so we saw this guy earlier when we talked about aromatics and benzene. If you have a benzene ring with an NH2, which is an amine, this has a sort of a historical name known as aniline. And if you look at this guy here, that is going to be aniline, and we would find our group by going really either way in this case. Will get us to 4-bromo aniline. Now, in a situation like this, if we look at our last one here, we still have aniline happening, and that is here. Obviously, this part. So that is our aniline part. But we also have here another group, which is this methyl, and that's the methyl group that's hanging there. Yeah. And you might notice that a little bit different in terms of how we give the location of that methyl group. Because that methyl group is not attached to a carbon, we actually don't use a number, right? So if this was attached to a carbon, we would use a number like 1, 2, 3, whatever it may be. But this is actually attached to a nitrogen, and sometimes with amines and amides, which we'll later see, they will use that N. And the N there refers to the fact that the methyl group is directly attached to the nitrogen. So if you see N-methyl, that means the methyl group should be attached directly to the nitrogen. If you see something like if you see something like N-methyl, or actually N-ethyl and methyl, they are both attached to the nitrogen. So if you had something like this, for example, this again would be our aniline part. But here again, we have a methyl that's attached to the nitrogen, and that is a 2-carbon ethyl group. And this would be something like N-ethyl, N-methyl aniline. So just like we would use numbers like 2, ethyl, 3, methyl, because those are attached to carbon, we use numbers to associate to the carbon chain. When they're attached directly to a nitrogen, you will oftentimes see this. So because amines, which we're talking about here, and amides are the only ones that have nitrogen groups in there, those are typically where you will see this. You could also see this as well, for example, and you probably won't maybe see it, but maybe somewhere along the way, maybe it might pop up. For example, if we had something like this guy here that we scribbled out. Now, if we didn't like name this guy sort of common name and went more of a systematic name or closer to an IUPAC name, we would actually look at these two things, and these guys would be named as groups. And this is actually the longest carbon chain. So another way of naming this, which again, we're not going to do in this class, but it is not the common way, but you would go, this would be N comma N, just like you have to give the number twice if it's 2 of them, right? And this would be a dimethyl ethane amine. And that is more of a systematic kind of IUPAC way of naming these guys. And again, you can see with secondary and tertiary amines, you sometimes will see those N's in there. And again, all you have to remember is that just basically means the group's attached directly to the nitrogen and not to the carbon chain. Okay, so let's take a look. Again, we look at the nitrogen here just for classification purposes. We got 1, 2, and 3 carbons. So again, this would be a tertiary amine. We're going to basically just find our groups here. So that is a 2-carbon group, which is a ethyl group. That obviously is a 1-carbon group, which is a methyl. And we got one more 2-carbon group on the other end there, which is an ethyl. We have 2 ethyls in the same compound, so that's a diethyl action happening there, right? We then will go methyl, and then a little amine at the end of it there. So diethyl methyl amine. Any questions on that one? All right, taking a look at this one here. That's a nitrogen with 1 carbon, by the way, and 2 carbons. That is a tertiary amine in this case. That, though, is a nitrogen or an amine group that's attached to a benzene ring. So that is going to give us our aniline. And that means that we do have one group attached there, which is a ethyl group. And that ethyl group, once again, is not attached to a carbon, but is attached to a nitrogen. So that's going to be an N-ethyl, just to indicate that it's attached directly to the nitrogen and not a carbon in this case. Any question? What's that? Correct. It was like these guys here. If that's what you're talking about. Yeah. Other questions? All right. So our line angle formulas here, obviously we could draw them just like everything else. Clearly here you do need to write the N, otherwise it's assumed to be a carbon. And this would be our primary amine, as that's 1 carbon attached to it, giving us a primary. This guy is attached to 1 carbon there and 1 carbon there, the nitrogen, which would give us our secondary. And this is 1 carbon here, 1 carbon there, and 1 at the end here, giving us our tertiary here. So again, if you were going to draw an amine using line structure, I would also take kind of the ether approach, is to start with nitrogen and then just attach the carbon groups as you need with lines would probably be the best way to sort of do that. And obviously to get our names here, this is 1 carbon, 2 carbons, 3 carbons. So that is propylamine. We have a 2 carbon group over here, which is our ethyl. We have a 3 carbon group over here, which is our propyl, and that gives us our ethyl propylamine. And lastly, we have an ethyl group there and an ethyl group there, which gives us our diethyl, and just a lonely line there, being our methyl group there, giving us our diethyl methylamine. Any questions on that there? All right, so let's talk a little about the solubility of amines and hydrogen bonding. As I mentioned before, because they do have hydrogens directly attached to a nitrogen, that's going to create a polar bond and allow it to participate in hydrogen bonding. And because it can participate in hydrogen bonding, that's actually pretty good, because then it can be fairly soluble in water as well. Water obviously uses hydrogen bonding, as we talked about, as its main source of interaction. So amines also use hydrogen bonding. So that makes primary amines and secondary amines with less than 6 carbons. Again, as we talked about, kind of that 5, 6-ish range is kind of where things start to go bad in terms of solubility. But if it's less than that, they should be soluble in water. They should be able to form some hydrogen bonding that's happening. Again, in this case, more positive, more negative. And again, if you have something like water here, more negative, more positive, you can do some type of hydrogen bonding. We'll just do it that way with it. And again, hydrogen bond in that sense right there as well. Tertiary amines cannot hydrogen bond, and that is because, a reminder, as we just saw, a couple of examples. If you have a tertiary amine, you got no hydrogens. So because it has no hydrogens, it makes it a little bit difficult for it to hydrogen bond. with like itself, but it can hydrogen bond with water, as is the water that is going to provide the hydrogen. So it's the water is going to provide the hydrogen to be able to hydrogen bond, but it cannot hydrogen bond, say, with itself, as it's lacking hydrogens to do so. But it can do that with water, as the water supplies the hydrogen. Because amines have that polar NH bond, they can hydrogen bond with water. Again, primaries can actually form more hydrogen bonds than secondaries. Again, as we've talked about, if you have a primary amine, that means your nitrogen's got a couple of hydrogens that both could hydrogen bond. If you have your secondary, once again, it has one hydrogen that could hydrogen bond. And again, a tertiary does not have any hydrogens, so it can only kind of hydrogen bond with water, as we just talked about there, kind of borrowing the hydrogen there from the water to do so. Like alcohols and smaller amines, the smaller the amines, including tertiary ones, are soluble in water and can form hydrogen bonds with water as well. In amines with more than 6 carbons, the hydrogen bonding sort of diminishes, and the non-polar part of the amine definitely gets in the way. So if you just kind of think about it here, just got a really giant amount of carbons everywhere. This big guy kind of gets in the way again for water to be able to kind of efficiently get in there to interact with the nitrogen. So again, solubility really starts to decrease. Pretty much like most organic compounds, the more nonpolar part you have, the bigger nonpolar part you have, you get what is referred to as steric hindrance, which is a fancy way of saying things just get in the way. So they're not able to kind of interact really well. You have these big parts that are not interacting and just sort of serve to be in the way of those type of interactions. Okay, so let's take a look. So the first one here is a primary amine. Again, we have the nitrogen directly attached to one carbon there. And that would mean that this guy right there has got a couple of hydrogens that definitely can participate in hydrogen bonding, which means I would think that guy should be soluble in water, fairly soluble in water, because it could do a lot of hydrogen bonding. It's definitely less than 6 carbons, so you're not going to run into any issues on that. Coming here to the next one, this is also an amine. It is a 1 and 2 carbon there. So that is a secondary amine. Also, ability there to hydrogen bond and should be soluble in water, also less than 6 carbons there. Lastly, this is not an amine, by the way. There's no nitrogen in that. That is our old friend from way back when. Right, that's just an alkane, right? So that is carbon and hydrogens all day. That is non-polar all day, right? And non-polar and water, which is polar, not gonna mix in this case, right? So this should not be soluble because of that, as obviously this is non-polar. It is going to, as we talked about, want to use dispersion forces. And water here obviously wants to use hydrogen bonding, right? So those are two very different sort of interactions, and they definitely will not be soluble in each other. Any questions on that there? All right, I think we're gonna lay it up there.